Michael's, but I couldn't do it justice. Okay, so take it away, Nigel.
You don't get the job of being the master of ceremonies at my daughter's publication. Okay, so the only way I can start off this lecture is to say the following. Now for something completely different. Okay, so you heard from David that logarithms, well, who cares about logarithms? And then today you heard from David, well, power laws don't believe in power laws because they're misleading. Everything I'm going to tell you today is all about logarithms. It's all about power laws. Okay, these are big deals in what I'm going to tell you about. The second thing is that the honeymoon is over. So the last couple of days I've been here and you've had David softening you up with nice movies and beautiful interfacial and hydrodynamic phenomena. You had Michael softening you up last night with the cooking and the recipes and the experiments and so on. All of that. All of that. So now it's going to be different. Okay? The honeymoon is over. We're going to be doing calculations. We're going to, there's even going to be exercises for the students. You're going to be expected to take notes and to really try to keep up with what we're going to talk about. So I've listed here the 3 lectures that I've been asked to give. So I was asked to give today a lecture in drag, a lecture on drag paradoxes and the renormalization group. And then next week I'll be talking about turbulence, introducing the concepts in turbulence, and then telling you about turbulence and critical phenomena and statistical field theory, and in fact some of the frontiers of the subject that we've been looking at. So, but today we're going to be doing something different. We're going to be looking at low energy molecule. Now, there is a theme to my 3 lectures. Okay, they're not just random 3 lectures just thrown together because Michael and Dan Lathrop asked me to talk about these things. There's a distinctive focus of these lectures, and that is the following. When I sort of told my friends back in Urbana that I'm lecturing at the Boulder Summer School of Condensed Matter Physics, people say, yeah, I'm not surprised, what are you going to be talking about? And I say, well, I'm going to talk about hydrodynamics. And they say, hydrodynamics? What's hydrodynamics got to do with condensed matter physics? In fact, actually in my department, nobody even knows what hydrodynamics is. In fact, how many people here are in the physics department and had a course in fluid mechanics? Oh, that's pretty impressive. Are any of you in the United States? Did any of you do your degrees in the United States? Wow, okay.
Of course, it's an engineering school.
That's an engineering school, okay, course in physics. So this is the sad fact that you can learn about black holes and what happens inside nucleons, but knowing what happens when you stir your coffee is an arcane subject that is not thought fit to be revealed to physicists, at least in the United States. France, it's a totally different story. But I'm going to show you in these lectures that there are strong connections between what's typically thought of as condensed matter physics in its core sense and fluid mechanics. And these connections arise in 2 distinct ways. So what I'm going to do in lecture 1 is I'm going to show you that there are non-trivial connections between low Reynolds number flow and critical phenomena. And in fact, the message of today's lecture is that things that are small are not necessarily negligible. So small does not equal negligible. That's the theme of today's lecture. In fact, what I'm going to do is I'm going to show you how one can solve problems in fluid mechanics using techniques that were originally invented to describe quantum field theories at high energies and condensed matter systems at their critical points. So we're going to be talking in the body of today's lecture about something called the renormalization group. Now, these lectures are intended for experimentalists and theoreticians, and also I want to point out that I'm aware that there is a high stress factor associated with the term renormalization. It's kind of like there's a kids' science fiction program called Doctor Who, and it's a sort of scary science fiction monsters, time travel kind of thing. And every week, before they air it, they issue the fear factor. They tell parents, this is the fear factor, this is how long your children are going to be hiding behind the sofa when they watch the program. Okay? So the fear factor for today's lecture is on a scale of 1 to 10, it's about 10. Okay? Now, I've already had several sort of rather worried inquiries about how much renormalization group theory you need to know in order to understand this lecture. The answer is none. Okay? So the good news is, no prior knowledge required. In fact, I would say that prior knowledge is a disadvantage. If you have been taught renormalization group and critical phenomena, and this is taught from my book, it's going to be a disadvantage. In fact, that's why I asked Leo to leave this afternoon, because I didn't, he's an expert in critical phenomena and physics. I didn't want to contaminate his knowledge of it. So he kindly stepped out.
Sure, can't contaminate it. It's not really sweet.
Yeah, that's right. I'm sure they will. So anyway, so you'll learn about this, and what you're going to learn is that the renormalization group is not the same thing as statistical mechanics. And moreover, it's not the same thing as quantum field theory. It was invented in those subjects, it's very useful in those subjects, but it's not the same thing. It has a broader generality, and that generality is sufficiently broad that we can use it to describe differential equations. So after today's lecture, you'll know, or at least you'll think you know, how to solve differential equations using the renormalization group. Just regular differential equations, like you did in high school, okay, but harder ones. Okay? So that's the first thing. The other thing that I'm going to explain is I'm going to explain drag paradoxes. So what do I mean by drag paradoxes? Now, this has nothing to do with the current political climate and any questions or things like that. This is to do with a fluid flow at low Reynolds numbers. And it goes back 150 years to Stokes. So Sir George Gabriel Stokes wrote down the Navier-Stokes equations. First thing he did when he wrote them down was he tried to solve the simplest possible problem that you could solve. And we're going to talk about that problem today. And what he discovered when he tried to solve that problem was that in fact he couldn't solve it. Okay? I mean, is it like a real disaster? You write down the equation of fluid mechanics that govern virtually everything you see in the universe around you, and you try to solve the simplest thing, and it's a complete failure. So why is that? So we're going to see that. We're going to see what goes wrong. And what goes wrong is incredibly subtle. It took 100 years after Stokes for those problems to get resolved. And the methods that were invented by the field of applied mathematics, created to solve the problems that I'm going to show you today, those methods are arcane. Now, some of you have heard about quantum field theory, you've heard about the renormalization group, and then you know it's got a reputation for being something that is really, really tough and hard to find diagrams and complicated integrals, and it's nasty. Okay? That's nothing. Okay? If you were a mathematician and you were brought up on singular perturbation theory, match asymptotic expansions, and all of that stuff, okay, that's far worse than anything that physicists invented. The mumbo jumbo that you need to solve these problems in the way that applied mathematicians solve them is incredibly arcane, requires lots and lots of cleverness, lots of mental agility, and again, it's very, very difficult to see how to do them in a systematic way. So what I'm going to show you, in fact, is something interesting. So the methods that were created to solve these problems, so this is essentially, in some sense, the entire field of applied mathematics, as it was sort of understood up to about 10 or 20 years ago, in fact even today in many universities. So these methods are things that most physicists have never heard of. These are things called singular perturbation theory, match asymptotic expansions, boundary layer theory, all of that stuff. It's also incredibly arcane. And what I'm going to show you is that all of this stuff is, in fact, oh no, I used the wrong chalk. Disaster. I got my own form, and you'll see why. And I'm now going to try to erase this. And it doesn't work. And my talk does. So this is basically a subset of a renormalization group. Okay? It's not equal to it, it can all be derived from it. So we're going to see that these two arcane subjects, one in mathematics, one in physics, are in fact related. Now the second connection that I'm going to make in these lectures over here is a different one. So the connection I'm going to make there is about statistical problems in fluid mechanics. So turbulence is a random chaotic motion of fluids. We'll talk in detail about it next week. But it's clearly something that's fluctuating, clearly something that you might say maybe a statistical mechanical approach would be useful. So people have tried to apply statistical mechanics to fluids, and they're fluids that are being driven, so these are far from equilibrium. Nevertheless, we're going to see that in fact there are all sorts of connections to critical phenomena. So I'm going to show you in lecture number 3 in particular that turbulence has many of the characteristics of a non-equilibrium critical point. And that's going to be recent work that we've done, and it builds on work that has been done over many years trying to connect field theory to fluid mechanics. Okay, so that's where we're going. So let's get started with some calculations. So I want to start off by telling you about drag. Okay. So what I want to do in this section is I want to show you how to formulate the drag problem. And I want to expose to you Stokes' solution and then Stokes' paradox. And then I'm going to use that to segue into part 2, which is basically how to solve partial differential equations by RG. So that's part 1 of the series lecture. This is part 2 of the series lecture. So let's start off then with a formulation. So what we're going to be thinking about is a simple problem where you have a sphere and it's in a steady flow with some velocity like this. The flow is going around it like this. And that's what Michael showed you about some of these problems. And what we're interested in doing is looking at the steady state and the Stokes equations. The steady state and the Stokes equations are just u grad u is minus 1 over rho grad p plus mu del squared u, where mu is mu over rho, and that's the kinematic viscosity, the molecular viscosity of the density. So let's now make a simple estimate of what these terms in the equation look like. So what we're going to estimate is the following. So we're going to estimate that u dot grad is basically it's u squared over some length scale. So this is going to be order u squared over L, where L is some characteristic scale involved in the flow. In this particular case, you might think that L is, say, something to do with the radius of the sphere. Then we look at the term nu del squared u, and what we estimate is that this is of order mu over L squared. So what we learn is that the ratio of inertial to viscous forces is basically u L over nu, and this is the famous Reynolds number that I'm sure you've already heard about. Now what we're going to assume is that we're looking at low Reynolds number flows, so we're going to assume that Reynolds number is very much less than 1, and so what we're going to essentially do is set it equal to 0. So what that means is that we're going to neglect this term in the naive-Stokes equations. So we're going to basically, this term is going to be, we're going to assume is negative. So what we then have is the following problem. We have that 0 is minus p plus mu del squared u, and then we also have the incompressibility of the fluid that says that del squared u, div u is equal to 0. Alright, that's the formulation, and there's a lot you can do with that, but we're only going to look at the simplest cases today, and we're going to look at the case of the sphere, and we're going to look at the cylinder. So let's look at those first. So we're going to start off with looking at the sphere. And the first thing we're going to assume is that the flow is steady. Which need not be the case. We may have all sorts of other flow phenomena that arise. We can have spontaneous symmetry breaking in this problem. What that means is that the solutions of an equation do not necessarily have to respect the symmetries of the full equation. So any given equation will have a whole bunch of symmetries, generally captured as Lie group symmetries. The solutions don't have to satisfy all of those. When that happens, that's called spontaneous symmetry breaking. So we may have solutions where the flow seems that it's just a steady flow flowing in like this, but actually what might happen here is in the wake of this sphere, we might get wakes, we might get vortices, we may get even turbulence. So we're going to, for now, we're just going to assume that the flow is going to be steady, and we're also going to assume that the flow is actually symmetric. So what we're going to assume then is that I can write the velocity field in the following way. I'm going to use spherical polars, so it's going to have a component ur, a component u theta, a component u phi, which will set equal to 0, and then ur will be a function of r and theta, and u theta will be a function of r and theta. So these are all in spherical polar coordinates, which you know how to write down, so I won't do a reason down. Okay, so that's the setup. Now, how do we solve these equations in this geometry with no stick boundary conditions? So I'm sure Michael told you last time the boundary conditions that we usually want to apply are no stick boundary conditions, and so we're going to use these. Now, what Stokes did was he introduced a function called the stream function. So what we're going to use is the stream function. And that's defined in the following way. We're going to define a function psi, and this function psi has the following definition. So u is equal to the curl of psi over r sine theta in the phi hat direction. So that's the definition of u, and what it means is, I write it down in components I get 1 over r squared sine theta d psi over theta, and u theta is equal to minus 1 over r sine theta d psi by dr. So that's the definition of what we'll call the screen function. Now, why do we call it the screen function? So this is where you have the first homework exercise. So this is something that you can all try to do because there's nothing out here to do on the weekends. So this is something to keep you busy because the mountains get in the way of the beautiful sunsets that I'm used to in Urbana-Champaign in the middle of Illinois. So what I want you to verify is that psi is constant on a streamline. And what's a streamline? So a streamline, that's a curve characterized by distance along the curve x. So x of s, which at any time t has the same direction as u at that point. So what that means is that if I think of the components of u as u, v, and w, that's how people conventionally write it down in fluid mechanics textbooks, then that says that dx by ds to u is equal to dy by ds to v is equal to dz by ds to w. All right, so you can go and check that. I'm going to just give you one more hint before we finish the exercise. So the hint is that if the local direction, let's denote that by E hat sub s, then you should be able to show that u dot grad u is equal to the absolute value of u, es dot grad acting u, and that is equal to the absolute value of u times du by ds. You can do the same thing for any scalar quantity f, which is defined on a streamline. So put, instead of u, put f there, and then you can show that if f is equal to a constant along the streamline, and that means that df by ds is equal to 0, because it means that as I go along the streamline, the quantity doesn't change. And that's what you mean by a constant. And so now the question is, here's this psi, the one I've just defined for you, so is u dot grad psi equal to 0? Okay. So it's a very straightforward exercise. So let's now work out what is the differential equation satisfied by the screen function. And so really, all we have to do is conceptually very simple, but the algebra is a bit of a mess. The algebra is simply to take the definition and substitute it into the governing equation of motion. I'm not going to do all the algebra in front of you, so let me just show you what you get when you try to do that. So this is just a sort of sketch. So what we do, so the strategy, so this is the end of this. So the strategy is to substitute the definition of psi into the equation of motion, and what we're going to use is the well-known identity, something in fluid mechanics gives rise to something called the Croco identity. So you use curl is grad div minus del squared, so then that says that you can write the gradients of pressure is minus mu times curl of u. And then it turns out that curl of u is equal to the following. You just calculate, and what you get is this. You get this formula, and this function e is defined in the following way. E squared is equivalent to d2 by dr squared plus e is minus sine theta over r squared d by d theta 1 over sine theta d by d theta. So that defines this differential operator E, and then curl U satisfies this equation. So now what you do is you simply calculate the R and theta components of graph P. So you can get that from here because it will curl, so I can calculate those R and theta components. And then what you say is d by dr of dp by d theta is equal to d by d theta of dp by dr. So you equate the second derivatives, and what you get then is the nice final equation of e before psi is equal to 0. So that's the equation. The boundary conditions are mostly boundary conditions. And so what you get is d psi by dr is 1 over r, d psi by d theta is equal to 0, and r equals a. That gives you two boundary conditions. We've got a fourth order equation here, so we need two more boundary conditions. And those boundary conditions come from the flow at infinity. So as r goes to infinity, we have that u in the radial direction should just be u cosine theta, and u in the theta direction should be minus u sine theta. In other words, what we're assuming is that here is our flow configuration, here's our flow, and then it comes round like this, and then eventually, once we get out here at infinity, the flow looks just like what we have coming in on the left-hand side. And so it's that's just the regular flow. So that's the assumption. And now the next homework exercise for you is to solve this equation. So I'm going to show you what the solution is, but I'm going to, for those of you who want to try your hand at it, give it a go. So exercise 2. So how do you solve? Well, the strategy is the following. So look at the boundary condition as infinity and translate it into psi. What you will get is that psi is of the form, I think it's this, a half u r squared sine squared theta as r goes to infinity. That's the solution in psi coordinates along the way away. So what you assume then is that we look for psi is equal to f of r sine squared theta. And now you can find the solution to this. So if you plug this in, and that gives you an equation for f. And it's not such a bad equation. You'll find it's not too bad. And then what you do is you look for solutions of the form r to the n. So you look for parallel solutions, and what you find, if you've done it right, is you should get n equals minus 1, 1, 2, and 4. So you've got 4 solutions, which means 4 quantities of integration. You've got 4 boundary conditions, and so you can find the solution. And if you do it right, here's what I think you'll get. You get that. Okay, so let's now calculate the drag. So that's the end of the exercise number 2. So what we do is, I first of all need to show you how to define that. Okay, it's kind of a mess, so what you do is we're going to start off very simple, make several steps. So step 1 is we want to work out what the drag is. So what drag is force equals A. So what is that? Well, the pressure is defined as minus the stress tensor at any given point times nk, where n is a unit vector to a surface. So this is the force in this area. And in terms of the actual pressure, the stress tensor, sigma ik, is given by minus p delta ik. That just says the pressure is isotropic. And then there's a term that depends upon the way that the flow is changing in space, and it turns out to look like this. And that defines the stress tensor. And so now I can work out what the force on the body is. And so what I have to do is do an integral of the stress, the force being in the area, over the entire surface of the sphere. And I'll just simply write down for you what the equation is. So this is step 3, this was step 2. So step 3 says that the force on the body, because I take the integral of the pressure around the surface of the body. So what I get then is I work out this formula, the R component of the stress tensor turns out to be this, minus P plus 2 mu dUr by dr. Sigma of r and theta is mu r d by dr mu theta over r plus mu over r dUr by d theta, and sigma r and phi is equal to 0. And then the pressure turns out to be the following. Now we can calculate the pressure as you go around the sphere. It looks like the pressure at infinity minus 3 halves mu u a over r squared cosine theta, and then I can calculate the net drag, and you get the following formula. It looks like this. With the integral from 0 to 2 pi d phi, integral from 0 to pi d theta, sigma r cosine theta minus sigma r theta sine theta, all evaluated at r equals a on the surface of the sphere, times the volume of integration, the measure, which is sine theta d theta d phi. There's my phi, there's my theta, there's the d theta. And if you go ahead and do that, then you get a very famous result, 6 pi mu u a. And that's the Stokes drag, which you've seen and heard. I've gone through this in this level of detail just to show you that it's intrinsically A, very boring, 2, not conceptually difficult, just involves a lot of calculation. So there's nothing intrinsically interesting about it. But so why did Michael ask me to talk about this? Good question, actually. Why did you ask me to talk about this? So let me show you now why it's interesting. Okay? So hopefully, so this is the worst part of the lecture. So this part is hard math fun, but it's not terribly interesting. But I want to show you that there are interesting paradoxes that arise from this. And these paradoxes turn out to continue. So the reason I dragged you kicking and screaming, or at least if you can kick and scream when you're half lulled into sleeping, but kicking and screaming to this point, then let's see what happens when we try to do something different. So let's now ask, that's fine, that was a sphere, let's now ask what happens when we look at a cylinder and we do the same thing. We're going to set the Reynolds number equal to 0, we're going to now do exactly the same calculation. Now, I could do the same calculation that I just did for you. All the algebra and all the special functions and everything like that. But I'm not going to do that, okay? Because you can see, just by being a little bit smart, that there's something fishy here that's not going to work for the case of a cylinder. So if I did that, what I'd end up finding is that I couldn't come up with any solution. In fact, Stokes didn't know this argument. Stokes went and tried to do all of this with a cylinder, which you'd think would be much easier because it's only two-dimensional, and it was a disaster. So let's try to see that there is a disaster here. So time to use the red chalk. Disaster. So why is there a disaster? So we're going to use dimensional reasoning. So what you heard in the previous lectures, why they didn't do all this whole applied mathematics stuff, is because they used dimensional reasoning and scaling and clever things like that in order to try to solve the problems that they were talking about. So now we're going to start returning to that kind of style, at least for a little bit. So let's work out what's happening. So what we're going to talk about is a cylinder. So we're looking at the drag of the cylinder. And of course, what we really want is the force per unit length. So we'll call this thing the net force. And what does the net force depend upon? Well, it has to depend upon a bunch of things. It's got to depend upon the radius of the cylinder, that we'll call A. It's got to depend upon the viscosity, mu. It's got to depend upon the density, which we'll call rho. It's got to depend upon the velocity at infinity, which we'll call u. So it has to depend upon all those things. Now, Michael, you talked to them about Buckingham's pi theorem, right?
It was in the book, I didn't say it, it was there. But, but you know, how about yes?
Okay, yes, so that's another thing I wanted to hear. So now we're going to use dimensional analysis, and in a form we're going to use it a lot in today's lecture. It's known as Buckingham's pi theorem, published in Physical Review, 1914 by Buckingham. It's a beautiful paper, definitely worth looking at. It's a classic. So what does Buckingham's pi theorem say? It says the following very simple thing. Dimensional analysis. It simply says that if you have something that is dimensionless, it can only depend on other dimensionless variables. That's called Buckingham's pi theorem. So what that says is that you take a physical problem, it may have lots and lots of different variables, you take that problem and you write it down in terms of dimensionless groups. Whatever you may want them to be, it doesn't really matter how you do it. You write down the dimensionless groups, and those are called pi. So for example, this problem, I'm going to call a variable pi naught. That's going to be the Reynolds number. That is nu A over nu. So nu, remember, is the kinematic viscosity. Another dimensionless group I can make is what I'll call pi 1, and that is the net force per unit length divided by rho mu u. And there's no other dimensionless groups. Those are the only two independent dimensionless groups I can make. I can choose them to be other things, but they'll all end up being combinations of these things. So I've got two dimensionless groups, so I know then that pi 1 must be some function of pi 0, where f is some function to be determined. So that's determined by solving the problem, which we're not going to do. Now what I want to do is I want to do exactly what I did for the sphere. So we want to solve what happens when Reynolds number is equal to 0, when we can ignore the inertial forces. And so then that says that pi 1 is equal to f of 0, and therefore is equal to some constant, whatever that may be. And so that then says that the net force per unit length is proportional to rho nu u. And that's our answer. We've used dimensional analysis to solve the problem. Miles better than doing all the stuff with differential equations and getting careful substitutions and changes in streamline variables and so on. There's only one problem. It's clever, elegant, did it only on one blackboard, but it's completely wrong. Okay? It's nuts. Because this says that it's independent of the radius of the cylinder. So, here's a question for you. Exercise number 3. Exercise number 3 is the following question. This argument shows you that there's something fishy about this problem, but here's the thing. Why did this argument not work for, or not operate for the sphere? So exercise 3. Why did this no-go theorem, as it were, not apply to the sphere? In other words, we did calculate.
That's pretty hard for an exercise. You get hard exercise.
We did succeed to calculate the drag on the sphere, no? So the question is, how come? Why? So, think about that. Okay, so that's the case of the cylinder. So the cylinder immediately goes pear-shaped from the time you calculated it. I just showed you the quick and dirty way to figure this out. But if you went through and did the calculation, you'd find you'd come to the same conclusion after much more pain and gnashing of teeth. So let's ignore that. Let's go on to the sphere, just like Stokes did. So then you say, well, I've done the sphere at Reynolds number equals 0. Let's have a look at the corrections to the sphere. The corrections for Reynolds numbers that are greater than 0. Still small, but greater than 0. So let's have a look at what's going to happen. So our government we started with the Reynolds number equals 0 case. And what we did was we ignored the u dot grad mu term. Okay? And that's of course why the stream function method worked. Because if you did the homework exercise for the stream function, what you'd have found is that u dot grad psi is equal to 0. So it took advantage of that. So you might say, okay, next best thing, we're going to use perturbation theory. So we're going to define a perturbation parameter, which is basically u dot grad u over nu del squared u, the absolute value of those things, and let's try to estimate what that's going to be. So what it's going to be is, again, u squared over r divided by nu u over r squared, and that is basically ur over nu, which is equal to the Reynolds number times r over a. And r here is the radial coordinate. So we could try to include this term by perturbation theory. Now, look what's going to happen. If you're going to use perturbation theory, then you assume that your perturbation parameter, which you of course made to be dimensionless, is going to be much smaller than 1. If it's not smaller than 1, it's not a small perturbation. Okay? So the idea is to use the zeroth order solution to work out what's going to happen. Now, let's have a look here. So let's suppose that r is just slightly greater than a, then indeed epsilon may be small. But as you go far away from the sphere, then of course epsilon diverges and goes to infinity. So in fact, what happens is as long as the Reynolds number is not equal to 0, there is no uniformly small, uniformly over the domain, no uniformly small perturbation parameter. And so I have a huge problem. I have a huge problem because near the sphere I can do perturbation theory, but far away from the sphere I certainly can't. And so I have a problem that we need to now go and try to address. So in a sense, what we've learnt is something I'm going to put up on the board as a kind of slogan. So basically, hydrodynamics at Reynolds equals 0 is not the same thing as hydrodynamics for Reynolds being very small. So there's a big problem here, and this problem is a deep problem. It's so deep that it took 100 years to solve. It's so deep that when the same problem arose in different disguises in other fields of physics, nobody recognized it was the same problem. And nobody recognized until very recently what the solution was. So, bear this in mind. We're finished with drag, we finished with Reynolds number flow, and now we're going to show you how we're going to get to the bottom of this. And the solution to this problem is very surprising. Right? It's not something that you're going to find is obvious. And in fact, the actual solution to this, how you actually do the calculation, I'm not even going to show you in this lecture, because even using the methods I'm going to explain to you is technically complicated. So remember, there was a boring bit in this lecture for about 10 minutes while I showed you all the substitutions I needed to do to solve the sphere at Reynolds number equals to 0. In mathematics, the algebra that I need to do to show you the correct solution to this, the best solution known to date, is terrible. So I'm only going to show you the general idea. At the end, I'll show you what you get when you actually try to implement it. So now we're going to change gears. So this is part 2. And now we're going to look at what I'm calling after Baumgart intermediate asymptotics of the second kind. And renormalization group. We're going to look at a fluids problem, but it's a fluids problem that is a much simpler one than this one. It's a more complicated one than the one we just talked about. Much more complicated, but the mathematical description is easy. So here's the problem. So this thing here is a sponge. Everybody see it? Okay, it's a sponge. But what a continuum mechanic would call this is an elastoplastic porous medium. Okay? What that means is that fluid can flow through it because it has holes. And it's elastoplastic because it has elasticity, but it also has plastic deformation. It can bend it, it will stay bent. In fact, it does more things than that. When you push the fluid through it, it will expand. When you squeeze fluid out of it, it will contract. But those processes are irreversible, and so there's hysteresis. So this thing does different things when you increase the pressure, it does a different thing when you decrease the pressure. So it's a weird kind of elastoplastic porous medium. Now suppose I had this in a fluid, and I asked you to work out the continuum mechanics of that. What that would mean would work out how the fluid flows through the medium, and work out the pressure and the velocity distribution throughout the fluid. I'm going to not ask you to do that, even as a homework exercise. I'm just simply going to tell you what is the governing equation. So the governing equation for the pressure in the elastoplastic porous medium obeys this equation. You're confusingly going to call the same variable u, but it's really pressure, not velocity. du by dt is 1/2 kappa d2u by dx squared times u. the diffusion equation. You've all seen that before. So, and that's achieved by what Simon Rushdie calls a process too complicated to explain. Okay. So, let's now talk about how you solve the diffusion equation. So what I'm going to do now is I'm going to show you how to solve the diffusion equation. And I know you know how to solve the diffusion equation, because you learned to solve it on your mother's knee. So what I'm going to do is show you a quick and dirty way to solve the diffusion equation using dimensional analysis. So let's start off with the statement of the problem. We're going to assume that at time t equals 0, our solution, our variable, is some kind of bell-shaped curve that looks like this. It has a width, which we'll call L, and it has an area under the curve, which I'll call mass, which I'll call m, which is the integral from minus infinity to infinity, u of x 0 dx. And we're just going to do this in one dimension. So just for the sake of simplicity, let's assume u of x 0 has the following form: m e to the minus x squared over 2l squared over 2 pi l squared square root. That's my initial condition. What's going to happen when I solve this problem in time? So you all know how to solve this problem, so I'm just going to write down the answer. The answer is that for t greater than 0, t greater than 0, what I have is that u of x and t is equal to m e to the minus x squared over 2 l squared plus kappa t divided by 2 pi l squared plus kappa t all square rooted. That's the solution for any arbitrary long time. And you've all seen that before. Now, okay, don't worry about that. I'm bound to get some halves and 2 pi's and things wrong. Don't worry about this. Okay, let's ask what happens now. What happens at long times? So the question is, what happens to t goes to infinity? So the answer is we simply set t equals infinity in this equation. And what we see is that u of x and t, as time goes to infinity, becomes m e to the minus x squared over 2 kappa t divided by the square root of 2 pi kappa t. Now here's something to notice about this. Of course this is very familiar, but you also notice that what I did is I took the solution as t goes to infinity. This is the same as if I had taken this solution here and set L to 0. If I took my initial condition, like this, made it thinner and thinner and thinner, keeping the mass the same, so turning it into a delta function, this is the same as the limit as L tends to 0 of u of x in t. And that's why we call this a similarity solution. So in this problem, the long-time dynamical attractor is the solution that you get from a degenerate initial condition. An initial condition where the width of the initial distribution approaches 0. Okay, so that's very simple. Now let's ask, what would we have got if we tried to solve this problem by dimensional analysis? So let's have a look. So we're just going to reboot and just do dimensional analysis. So what we're going to do is the following. We're going to write down the dimensions groups. So pi is one of them, which is this u of m root kappa t. That's dimensionless. Another one I can write down is pi 1 is x of the square root of kappa t, and another one I can write down is pi 2, which is L over the square root of kappa t. What does dimensional analysis tell us? Dimensional analysis tells us that one of these must be a function of the others. They're all dimensionless. So what dimensional analysis tells us is the only thing it tells us is that pi is some function of pi 1 and pi 2. Now, over here, we were interested in the question of what is the long-time behavior of this initial value problem. And the initial value problem is now encapsulated by these dimensionless groups. If you want to ask what is the long-time behavior, the long-time behavior, or equivalently the R goes to 0 behavior, is all captured by setting pi 2 equal to 0. So t goes to infinity equals then L goes to 0 equals pi 2 going to 0. So all we have to do is say that at long times, this is now some function of pi 1 and 0, and in fact f of pi 1 and 0 is just, we can call that a new function, let's call it g, pi 1. So now what we can say is, well, that means that u of x and t is n with the square root of kappa t times this function g, which we don't know what it is, of x with the square root of kappa t. Now, if we take this and substitute it into the diffusion equation, we get an ordinary differential equation for this function g. So, next step, sub this into the diffusion equation. And that gives me an ODE for g as a function of its variable z, where z is x with the square root of kappa t. And what is that function? It's this g double prime plus z g double prime plus g is equal to 0. G goes to 0 as argument goes to infinity, and the solution to this differential equation is easy. It's e to the minus z squared over t. So by using dimensional analysis, I can solve the problem, and everything is fine. Now, the actual problem of the sponge, the actual problem of what happens with this border razor is not the one that I just solved for you. What I just solved for you was the diffusion equation. But this is an elastoplastic porous medium, and that means that it has hysteresis. That means that when the pressure increases, it does something different than when the pressure decreases. So actually, I tricked you. The right equation is this one. du by dt is equal to d kappa dx squared u. But now d has the value 1/2 when dx squared u is positive, or du by dt is positive, and it has a different value, which I'm going to write suggestively as a half into 1 plus epsilon, when dx squared u is negative. So this fact here, that the diffusion coefficient changes sign, not changes sign, changes its value, when dx squared changes sign, that's the hysteresis that's involved in this problem. And because of the way it works out, you might think, oh, this really happens inside the del squared, but in fact it happens on the outside. So it really is this equation that I was going. And this equation is called Boundless equation. So now let's work out how to solve Boundless equation. So this is 3. Solve Boundless equation. Well, it's very simple. Let's look at what dimensional analysis tells us. It says that pi is equal to u over m, u kappa t. Pi 1 is L with the square root of kappa t. and 2 is x over the square root of kappa t. And then I've got to apply 3 because of the way that I defined my factor that comes out in front here. I have a new parameter, which is this epsilon. And this epsilon, it doesn't have to be small, but in a few minutes I'm going to assume it to be small. This parameter epsilon is dimensionless, so then we get it like that. So now you say, well, this is great. What we have to do the following, so that this says that u is equal to n with the square root of kappa t times some function of x with the square root of kappa t over the square root of kappa t and epsilon. And now what I have to do is if I want to know the long time limit, what I need to do is set this term to 0, like I did before, and so that tells me that u is equal to n over the square root of kappa t times some g of x over the square root of kappa t, a function that has to be defined and determined, but also a function not only of this, but of this variable epsilon. That's what you might think. That would be a very sensible thing to do, and it turns out to be utterly wrong. Okay? Okay, now, why can this be wrong? How can dimensional analysis give us something that is wrong? Let me first of all tell you how I know that it's wrong. And you can check this for yourself. So this is going to be the next exercise. How do we know? So here's how you're going to solve this problem. What you do is you say, well, this is very simple. What you do is you do exactly what we did for the diffusion equation. So you take this form here, you get it down to this function g, the scaling function, then you find an ordinary differential equation for g. So what you do is you compute the ordinary differential equation satisfied by g. And so what's that going to look like? Well, let me help you here. So here is the variable z, which is x over the square root of kappa t. Here there's the function u. You know, it's some kind of bell-shaped curve, so it looks something like this. So then that's what we expect it to look like. Now, what do we know? In this problem, we know that the diffusion coefficient changes its value where d2u by dx squared changes sign. So what's going to happen is over here we have dx squared u positive, over here dx squared u is negative, over here on this line dx squared u is equal to 0. And now when I substitute this ansatz into my partial differential equation, I'm going to get two ordinary differential equations. I'm going to get one differential equation for here, and I'm going to get another differential equation over here. So I'm going to get an ODE1 over here, ODE2. Now what do I want? Well, what I want is at this point here, where these things overlap, this point here, what I want to do is I want to match first and second derivatives. And I want to do that because I have a continuous current physically. And so I could go and try to do that, and what you're going to find is that you can't do it. What you get is an equation that says 0 equals 0, or something like that. Or worse, 0 equals 1. Okay? You can't do it. So then you say to yourself, well, that's pretty bad. I know the other way out of this. This is what physicists always do when they don't know how to solve a problem. They say, the problem is ill-posed. Actually, there isn't a solution. Okay, it was a trick. Actually, that's not the case. So pure mathematicians come to the rescue here. Pure mathematicians are very valuable. And in this particular case, Renormalization in 1958 proved the uniqueness and existence of this particular problem. So this PDE does have a well-defined solution which is, has continuous first and second derivative, it exists and is unique, satisfies all the boundary conditions. So you know that there is a solution. But this is not it. So, what is the actual solution? The actual solution is remarkable. The actual solution is the dearest thing I can find in the world of differential equations to the critical exponent that you get as a second order phase transition. And the actual solution is this. U of x and t looks like this. It does have a function g, and x over the square root of t. It does depend upon epsilon, just as we said. It does have something in front, and it does depend upon t. But it depends upon t in the following way. T to the 1/2, but there's an anomalous dimension, a plus alpha. And this alpha is what's called, if this were a field theory class, we would call this an anomalous dimension. More interestingly, this epsilon, this alpha, is not just a number, like 0.326 or something like this. This alpha is a function of epsilon. And what I'm going to do is I'm going to show you why this is true, and I'm going to show you how to calculate this alpha. So the questions that you have in the following question are, how do we know this? And the second question is, how do we calculate alpha as a function of epsilon? And there's a third question. The third question is, how can we easily understand this result? And there's a fourth question. And the fourth question is, what does this have to do with drag? So I'm going to start from the bottom up. What I'm going to show you now is what this has to do with drag, and in fact what this has to do with the way that we solve problems in physics. Then I'm going to show you a simple three-line argument that derives in a heuristic way that will satisfy 99% of you in this room for 99% of the time, how you can obtain this result. And then I will show you at the end, trying to skip as much as I possibly can, because I don't like doing calculations every morning, you like seeing them, how we actually know this is true and how we can do this systematically. So let's take it from the bottom up. So let's start off with dimensional analysis. And in fact, the question I want to ask is, why did dimensional analysis fail? And this is actually an interesting question. I remember my shock when I was learning quantum field theory and statistical mechanics as a graduate student. And I was reading these books that, oh, these are deviations from dimensional analysis. And I was scratching my head and thinking, how can dimensional analysis be wrong? It can't possibly be wrong. And yet that's what I was reading in these quantum field theory papers. It made no sense to me. Well, dimensional analysis can't be wrong, but we can use it. We can overuse it. So let's think about what we do with dimensional analysis. So what we do is, it's not wrong, but we overextend it. And in fact, let me show you what we do. What we say is, well, some pi is some function of bunch of dimensionless groups, so whatever it may be, and let's say pi naught, for example, is the radius of your experiment divided by the radius of the galaxy. Basically say, well, the radius of my desktop experiment divided by the radius of the galaxy is really small, so I can neglect that. So let's suppose that pi naught is very, very small, and we set pi naught equal to 0. So then we say, okay, that's fine. Pi is f of 0, and 1 up to pi n, and now we've made the problem easier. It is easier. That's true. We've got one less variable to deal with. But we've made a very strong assumption. The assumption that we've made is the following. We assumed that the limit of pi 0 tending to 0 exists. Okay, so you say, well, okay, mathematicians have to worry about that, to dot the i's and cross the t's, but physicists never have to worry about that. That's completely wrong. All of the problems that you learned as an undergraduate and in graduate school, all of those problems are very carefully chosen. They're the ones for which this limit does exist. All of the problems that we can't solve or find difficult to solve, like critical phenomena, like turbulence, like phase transition kinetics, and so on and so forth, all of those problems are the ones where this limit doesn't exist. We only teach you the easy problems, because those are the ones that we can solve. Those are the ones where this works. So let's ask them, how can this fail? How can we classify the breakdown of this assumption? So Barenblatt and Zeldovich proposed the following classification, and it goes something like this. Type 1 asymptotics, common sense asymptotics. That's the kind of asymptotics problems where as you take the limit exists, everything is fine, you can solve the problem. So problem 1 is that the limit exists, everything is fine. Problem 2, or category 2, is where the limit doesn't exist, and it doesn't exist in the following interesting way. But pi breaks down the following way. It's pi naught to the power alpha times some function, which we call g, of pi 1 over pi naught to the alpha 1, pi 2 over pi naught to the alpha 2, pi n over pi naught to the alpha n. This is a way that assumption can fail to exist. Because clearly, as I take the limit, pi naught goes to 0, this thing goes to 0, or maybe it goes to infinity, depending on the sign of alpha. These things also define things. So that's one way. Now, why this way? Well, this is what happens in quantum field. This is what happens in phase transitions. And this is what happens in the Barenblatt equation. Now, how do we solve these problems? You said, well, it's easy, right? Because you've got these exponents, alpha 1, alpha 2, up to alpha n. We've got those exponents, and we know how to solve for exponents. All we have to do is do dimensional analysis, just like I've been doing up to now in class. Except dimensional analysis isn't going to work. Dimensional analysis is not going to work because everything here has got no dimensions. All the dimensions have been taken out. So we can't get alpha 1 up to alpha n by dimensional analysis. We have to do something smart. Okay. There's a third class of problems, which are none of the above. These none of the above problems have the limit as pi naught goes to 0 in totally different ways. They do it in a plethora of different analytic forms, different ways that the problem can become singular. Those problems turn out to be singular perturbation theory problems. So it turns out that all these problems here, in class 3, are examples of singular perturbation theory, and these include the Stokes problems. They're in this category. That's the functional forms are much more complicated than the one I'm going to show you. The method that can solve this problem, which I'm going to show you now, the normalization group, solves these ones and all of these. It solves all of these. It unifies the way we understand these things. But I'm only going to show you it for this class of problems because it's much easier to do. So that's what we're going to do. Now, that's the connection with drag. The drag problem is one of these. The way to solve these things is by a normalization group, and I promised you didn't need to know a normalization group to do this lecture. And I'm now going to show you a simple argument for showing you how this problem solve, and then I will end by showing you a sketch of how one would go about this using the renormalization group method, and the details are in the notes. So this is the part that you want to stay awake for, because in the next 5 minutes you'll understand everything about where anomalous dimensions come from, how renormalization group works, and you'll understand it much better than if you had sat through 20 lectures of a course on particle phenomenal renormalization group, where you have quantum field theory and gauge invariance and all sorts of functional intervals and things to do. So let's have a look then at the heuristics of this problem. So next thing I'm going to solve then is the heuristic derivation. So let's do a bit of physics. Let's think physically. Everything goes wrong when epsilon is non-zero. So let's do the following. Let's make epsilon to be very, very small. And let's think physically what's happening here. So what's happening physically? Now, this is a diffusion problem, and diffusion problems come from the conservation of mass. You know how to derive the diffusion equation. You have a variable that has a conserved current. Du by dt is div j. So that's the conservation law. You say that the current is minus the gradient of the concentration, and that gives you du by dt is equal to delta speed, and then there's a diffusion coefficient that comes in here. So it all comes from conservation of mass. This equation, the Baumgarten equation, is none of this form. It doesn't conserve mass. So the B equation does not conserve the mass. What I mean by mass, remember the mass was the integral of the area under the curve. You can see that, you can try. Can you derive from a form like this an equation that has a discontinuity in the diffusion coefficient? No, you can't. Not if it's local. If it's non-local, you can, but that doesn't count. It has to be a local conservation. So this equation doesn't conserve mass. So what that says is that if I compute m minus the integral u connection to dx, in the diffusion equation, that's equal to a constant. But in the Baumgarten equation, it changes in time. Mass gets removed. There's another version of this equation, another derivation of it, which talks about the flow in a porous medium. Now what happens is this. When fluid flows into an empty pore, it fills it up. When fluid flows out of a pore that was initially filled, it comes out, but it leaves a thin wetting layer around the edge of the pore. And so as you track the fluid flowing through the porous medium, you suddenly discover that some of your fluid is disappearing. It's like the missing mass of the universe. It's all lost in wetting layer around the pores of the porous medium. So that's what's happening here. The mass is not conserved. And so that says that that's what's the problem with this equation. Let's suppose that epsilon is very small. If epsilon is very, very small, then m dot is going to be small. And so we might say that adiabatically, the solution that we got for the diffusion equation will look the same, it's just that the mass will change with time. So adiabatically, what we would expect is that u of x and t looks just like what we had before. So e to the minus x squared over 2 kappa t plus l squared over 2 pi kappa t plus l squared, square rooted, and then we multiply by the mass, but now this mass is time dependent. And the variation of this with time is fast, so that adiabatically the solution always looks like this. So now the question is, what is the equation for m of t? So that's what I want to show you next. So let's have a look at the following things. So here's m of t as the integral from minus infinity to infinity u dx. What does u look like? So what we have is the following. U as a function of x looks something like this. And this is where it changes, the derivative changes sign. This boundary here is of x of t, and this boundary moves like the square root of 2 kappa t plus l squared plus some corrections that are due to order epsilon. So if I had just a regular diffusion equation and asked where does dx squared u equal 0, it would be at this point here. Okay? If I now plot what the diffusion coefficient looks like as a function of x, that looks like this. It's one value over here, another value over here, and there's a discontinuity there. So I can write the solution in the following way. I can say that dm by dt is just put a d by dt in front of this, a d by dt in front of this, and so what I get then is the integral of d of x dx squared u. Now how do I do that integral? Well, I'm going to do it by parts. So this is minus the integral of dd dx. I integrate my parts. Now if d looks like this, then dd by dx, the diffusion coefficient changing, is going to be a delta function situated at x of t. So this is then just epsilon times kappa dx du by dx evaluated at x of t at time t. And we can do that differentiation because we know what du by dx is. U looks like this. So when I differentiate with respect to x, I have this term here gets brought down. It gives me a factor of 2x in front with these kappa t plus L squares down here. So I get the factors of that. And then I substitute into x the position of the moving boundary, which is the square root of kappa t plus L squared. So this evaluation, this derivative you can do in your head, and it looks like this. Minus epsilon kappa m of t, and then I get root 2 pi, that came from the root 2 pi in front, and then I have 1 over kappa t plus L squared, and it's raised to the 1th power, and then I have this term here, e to the minus x squared over 2 kappa t plus L squared. I put in x squared is equal to kappa t plus L squared in here, so the x squared, kappa t plus L squared cancels here and cancels here, and what I get left with is a 1 and a 2 up there, so I get an e to the minus a half. So I get a 1 over root 2 pi e, it comes in here like that. And this is the equation for dm by dt. It's just a very simple ordinary differential equation. dm by dt is n over t with a bunch of constants in front. So that's easy to solve. You can all solve that in your sleep. And what the solution is m of t is equal to m initially times L to the power 2 alpha over kappa t plus L squared to the power alpha, where alpha is equal to epsilon over the square root of 2 pi e. That's this factor out in front here. So m of t looks like this, and now what I have to do is, since I know what m of t is, I just have to substitute it into here, into my answers. So that then gives me my final form, that u of x and t is equal to naught L to the power 2 alpha over kappa T plus L squared to the power 1/2 plus alpha e to the minus x squared over 2 kappa T plus L squared. And if I want to take the long time limit, then what I get is that u of x and t goes like m0 L to alpha kappa T to the power 1/2 plus alpha e to the minus x squared over 2 kappa T. Now this is fantastic. Okay? Why is this fantastic? It's because even as t goes to infinity, I still have L here. I had to have L there. Why? Well, because I told you on the previous blackboard I made the ridiculous assertion that this scaling went as kappa T to the power 1/2 plus alpha. And you should immediately have all jumped up and said, no, that's impossible. It violates dimensional analysis. Well, it doesn't violate dimensional analysis as long as you have this term here. So this thing says that this has a very sensitive dependence on the initial condition. In the diffusion equation, I start off with my stuff that starts off 1 centimeter wide. I wait for 100 years, and it diffuses out 100 miles. And I can't tell what the initial distribution is for the diffusion equation. For this problem, for this boundary equation, this thing starts off 1 centimeter wide. I wait 100 years, it diffuses out 100 miles, and it never loses the memory of its initial condition. That's strange. That, the fact that L is present, even though time is not infinity, is called scale interference. Here is a ludicrously small scale that still interferes with the solution at arbitrarily long times. Now, what does this have to do with critical phenomena, you might say? Well, I'm now going to have to tell you something about critical phenomena. If you've had a course in critical phenomena, you may know this. But let me tell it to you nonetheless. So in critical phenomena, you look at statistical fields, the order parameter, fluctuating on a lattice. So I'm now going to tell you about the connection to critical phenomena. So in critical phenomena, you have an order parameter. 5. And you write down a Landau-Ginzburg free energy for it, and you do functional integrals, and you calculate the base energy dependence, and so on and so forth. Some of you have seen all of that, and what you do is you look at its Fourier components, phi k. It has Fourier components, and what one looks at is the 2-point correlation function of an order parameter. So you might typically look at something like this, phi k squared phi. And this thing is called usually g of k. And why do we look at this? This is because whenever you do any experiment in condensed matter physics, you're usually doing a scattering experiment. Any kind of observation requires scattering. Even if the scattering involved is just the light scattering off the needle in the voltmeter into your eye. There's always some scattering processes involved. So you always measure 2-point correlation function. And if you go and look at page 168 of any good textbook on critical phenomena, you will find that at the critical point, there is anomalous scaling and g of k at t equals tc scales as k to the minus 2 plus eta. And eta here is an anomalous dimension. It's a kind of critical experiment that people like to try to calculate, and that Ken Wilson got the Nobel Prize in Physics in 1983 for figuring out how to do it. Now, if you also look in the textbook on critical phenomena, what you'll find is an attempt to do dimensional analysis. So dimensional analysis on the field theory. And I'm just going to tell you the result. You don't need to know how this is done. You can read it if you want, but you don't need to know. So if you work it out, you can work out the dimensions of the order parameter phi, and once you've done it properly, it has dimensions of length to the power 1 minus d over 2. So that tells you then that the dimensions of the two-point correlation function have to be, when you do Fourier transform of this and substitute it into here, have to be length squared. There has to be a dimension for two-point correlation function. So, that's fine, that's what you get, but then, oh no, you have this. You know, k to minus 2 plus eta is what you find for the behavior at Tc. So this is why they say that at a critical point, at Tc, dimensional analysis is violated. It's not true, so I'm putting quotation marks around it. So what's really going on? Well, what's really going on is the following. In critical phenomena, you have your statistical fields, you have your order parameter defined on a lattice. Typically, that's because what you're looking at is, say, a magnet or a superconductor or something like this, and it's defined on a crystal lattice. So you have a lattice with some scale L, and then you have the range of correlations of the order parameter on that lattice, and that range of correlations have many lattice spacings. So this is the correlation length, and as you go towards Tc, the correlation length goes to infinity as t tends to Tc. That's the origin of critical phenomena. Now people always say, well, critical points, the only important length scale in the problem is the correlation length. And they say that because the correlation length is going to infinity as you go close to critical phenomena. If that were true, if it were indeed true, that the correlation length was the only length scale present in the problem, then you would never have anomalous dimensions, you'd never have critical phenomena, and you'd never have interesting physics here. The reason the critical phenomena problem was so interesting is because until it was solved, there was no way, even in principle, known to explain why you could have an eta that is non-zero. Now, here's the solution to the problem. Here's what actually happens. In critical phenomena, what happens is you get scale interference. In critical phenomena, what happens is that even though the lattice scale is angstroms and the correlation length is miles, you still retain a memory of the small scale structure of the statistical mechanics. That is to say, you still remember the lattice. So in fact, at Tc, when you do the problem correctly, g of k is like L to the eta, k to minus 2 plus eta. The system does not lose memory of the underlying lattice scale L as the correlation length goes to infinity. So this is again scale interference. This is scale interference, but it's scale interference in space. Over here, we have scale interference, but over here in the Baron-Van equation, it's scale interference in time. But it's exactly the same phenomenon, and it's exactly the same process. So now you know the most important things that you need to know about scaling and the critical phenomena. Now, in my notes, I have a sketch of how you do the calculation systematically. I showed you this heuristic, and I think that's good enough. Now you understand the basics of this problem. How do you solve this how you solve this technically, what you would do is the following. You write down the solution to the differential equation in terms of Green's functions. You write it with a Green's function on the left-hand side being the Green's function for the diffusion equation, and on the right-hand side you have your perturbation, which is proportional to epsilon. You then solve it by Green's function methods, and you end up with a perturbation series in epsilon, and that perturbation series diverges. The perturbation series diverges because every term in the perturbation series, apart from the first one, exhibits logarithmic divergences. And it's not trivial to see that mathematically. So I don't want to do the math for you. Although it's in the notes and you can work on it over the weekend if you want, and if you're interested I can show you. But that's what happens. Now the reason that you get these divergences in the perturbation theory, I'm going to explain to you physically in ways that you can remember. So David told us that logarithms don't matter, and the power laws don't matter, and of course I understand and appreciate fully the context in which he said that. But for people who do field theory and critical phenomena and partial differential equations and so on, these things are very important. Why are they very important? So now I'm going to tell you about the formal theory. The formal theory is you take the equation of motion, you write it like this, and then on the right-hand side you have stuff that depends upon epsilon. And you solve by Green's functions. This operator on the left-hand side is the diffusion equation. And so when you invert this equation, you solve it by Green's functions, you're iterating using the Green's function for the diffusion equation. Inverting the stuff that's on the right-hand side. Now, the diffusion equation conserves the mass of this variable. But the actual equation doesn't. So order by order, as you work out the terms in the perturbation series, you're calculating then from a Green's function that came from the diffusion equation, and the Green's function thinks that everything is conserved. But the real equation says no, it's not conserved. How can the perturbation theory register its objections? So the logarithmic divergences of the terms in the perturbation theory are cries for help. That's the way that the perturbation theory says, this is broken down, this isn't working. Your starting point of your perturbation theory is absolutely wrong, and the way that the theory breaks down is an important indicator of what you need to fix in order to make the theory work. So the logarithms and the logarithmic divergences of the perturbation theory, so perturbation theory terms, not the whole perturbation theory itself, but the terms, diverge, and the way that they diverge tells you how to fix at the starting point. So the renormalization procedure is a clever way to look at the breakdown of the perturbation theory, look at its failure modes, deduce from that what you should have perturbed about, not the diffusion equation, but something else, something close to it, in order to get something that converges. So what the technical wizardry of the renormalization group is that it interprets the breakdown of the terms of perturbation theory and uses that information to fix up the perturbation theory, so that order by order in perturbation theory, the terms don't diverge. And nothing depends upon the way in which you fix up the theory. So if you want to read about that, you're welcome to do so. Those are in the notes, so I'm not going to go through them. Alright, so I'm finished. What I want to tell you about is just a couple of last things. So this whole method can then be applied to things like the drag. And it's technically complicated, but conceptually it's nothing more than what I told you today. That's the first thing. Secondly, it works really well. Okay, what I mean by that is the following. Let's suppose you take a problem, some very complicated perturbation theory problem, with a smooth parameter epsilon. And you say, how do I solve this problem? One way you can solve it is by doing matched asymptotic expansions and other techniques. If you're really clever, you're going to be able to solve the problem. But if you're really dumb, like me, like a physicist, I just want to turn the crank, find the answer, get on with life, it's not going to be good enough. The normalization group method, on the other hand, you just turn the crank, you do the recipe, just follow the thing, and it just works. And it automatically generates for you all the weird non-analyticities and strange functions that come up in the regular solution of these problems. So in the Stokes problem, the solution that was discovered in the late 1950s was an incredible solution. It involves power laws and logarithms and powers of logarithms and things like this. It's a miracle that anybody figured that out. All of that just drops out very smoothly and algorithmically when you do this renormalization procedure. The other thing that's great about it is that it works well in the following sense. Most perturbation expansions, when epsilon is not small, the solution, the approximate that you obtain, doesn't work very well. It doesn't fit very well in the normal solution. The normalization group methods, their solutions are more robust. And the reason that they're more robust is because they involve a sort of summation to all orders of the perturbation theory of the solution, the Green's function solution, and so they're kind of non-perturbative. So they work even when epsilon is large, much larger than you would guess from the regular expansions. Moreover, you can derive the normal result of the applied mechanics calculations very simply from the renormalization calculations. So technically, that's how you solve those problems, but of course, there's way beyond what I can do in this time analysis. So I think I'm going to stop there. I'll be happy to take any questions and then how much success you have in doing the homework.
And are you going to grade the homework?
You're going to grade it, right? That's what you said, right?
I won't be here though next week.
That's right, we'll mail it to you.
So, you've all been very quiet.
It was very difficult.
It's very difficult, yes, it is. It's not easy. It's not easy to learn about the hardest problems in applied mathematics and the hardest problems in theoretical physics in 1.5 hours.
And I don't think I still understand why that limit sometimes doesn't exist.
It sometimes doesn't exist.
Yeah, you said that you're going to say what, there are times that it doesn't exist.
There are times when it doesn't exist, yes. It just is, it's just life. Some limits, if I have the function a plus x squared and I take the limit a goes to 0, that limit exists. If I have the function, x times e to the minus 1 over x, and I take the limit x tends to 0, something different can happen. So not all limits exist. Sometimes they go up, sometimes they go to 0.
But you can say it in a way that is less negative. So there's no reason that something shouldn't depend on initial conditions. It's a miracle that the solution doesn't depend on initial conditions. And as long as you're okay with that, there's no problem.
Well, I don't agree with that. And the reason is, that if I say to you, the ratio between the size of an apparatus and the radius of the moon is a very small quantity, nothing should depend upon that. That's counterintuitive. So I think experiment is genuinely counterintuitive. And so it's just like when you learn quantum mechanics. If you give a quantum mechanics lecture, and how do you know when the lecture is a success? If the lecture is a failure, everybody comes out of the room saying, yes, I understand quantum mechanics, that's fine. Okay? And now, when you succeeded in explaining quantum mechanics, and everybody leaves the room saying, boy, I don't understand that at all, it's totally weird. Okay? So you shouldn't understand this. You can't understand what I told you just from following this. That doesn't mean that you won't be able to understand.
Okay, good. So
you've
stimulated the audience, so there are several questions.
Good.
When you do dimensional analysis, I don't understand how you can pi, pi1, pi2. Just by staring at them, I can come up with maybe other non-dimensional.
Yes, there's no unique way to come up with the dimensions of groups. You just have to look at the dimensions of things and group them any way you like. The ones that I wrote down, you could look at the thing and come up with different dimensions of groups. I could take your dimensionless groups, multiply those two numbers together, and get my dimensionless groups. So there's no unique way to do it. I happen to choose the nicest, most sort of physically appealing ways to do that, to make it pedagogically nice. Okay, so it's not unique. Yes.
You said over there that the units of the order of parameter are L to some power. Is that like a generalized L? Or,
Well, so you have to write down your Landau theory of phase transitions, and then you have to scale things out in an appropriately sensible way, turn it into a dimensionless statistical field theory. And when you've done that right, then that's what you find.
Okay.
So that's explained in chapter 7 of my book. Okay? It's not, I say this, of course, it's kind of a joke, and it's not meant to be self-promotion. But these things, when I learned this stuff, I found it very difficult. It was never explained in the papers of course. So it's a real sticking point. So I tried to explain that, how do dimensional spaces stack up, and how these things come. So chapter 7. So, 2 more questions.
So you're trying to solve the parental equation. So you're setting up a perturbation theory in terms of epsilon, right?
Excuse me?
You're setting up the perturbation theory
Yes.
in epsilon.
Yes.
Then if you have to sum in all orders of epsilon, that should be difficult. I mean,
It is difficult.
it's like solving in all orders of alpha.
Yes, so let me thank you for the question. So what the renormalization group does is the following. And you're going to have to look at the notes to do this. It's not worth me explaining it to you now because it's, it'll just okay? But you now all know enough that you can go and look at the notes and you can sit down and in half an hour just work through the calculation. Okay? Now, what does it do? Everything you do by renormalization group, you can also do by any other method, by any other trick method. For example, you could say, take the terms in the perturbation theory I get by writing down the integral equation. First order term is finite. Second order term has a logarithmic divergence. Third term, God, it's an awful mess. Let me try to find the most divergent piece of it. If I go and do that, I find I get the first term squared. Third order, terrible mess, diverges in lots and lots of different ways, but the most divergent bit, as time goes to infinity, or as L goes to 0, turns out to be the cube of the first term, and so on. So I can then sum those logarithms like that. The renormalization group process doesn't need you to do that. It applies a functional constraint to each order of perturbation theory. So I just have to go to the first order of perturbation theory, and then say, look, my solution doesn't satisfy a particular functional constraint. It has to apply to the perturbation theory. Let me go and apply that. And the magic of it is that one equation has the effect of summing all the orders in the perturbation theory. I get an approximation that came from my first order perturbation theory. So the normalization group used in this guise is a way of, quote, improving perturbation theory. If I go to first order perturbation theory, I can give you the improved solution, which is the one that we derived heuristically. If you calculate the second order perturbation theory, turn the crank, I will get an improved version of the result for alpha and for the function, the scalar function g, better than the one I showed you heuristically. So it takes each order perturbation theory, puts it all together, finds a non-perturbative functional constraint which mixes up all the orders of perturbation theory, and that's what it gives you.
So, is this a quick question?
Yeah. So what if the initial condition for the variable equation is a multi-pole state with different length scale? Then how do you go to do it?
So again, so you're going to just start off with some solution, some initial condition which has got some compact support, okay? Then again, you have to, just like say when you solve the diffusion equation, a very lot of times, basically the Gaussian solution is the one that survives, and all the other terms die away or some dominate. So the same thing happens.
So, I would like to propose that we first clap.